Okay, so today's lecture is on angle chasing, and you attend. I think the last geo class we had was of Rohan's, the first class in OMC, and we just basically discussed a few things like what centers of triangles are, what, and I think he assumed that you know about cyclic quadrilaterals, and we discussed Simpson line and I think a few problems from what I remember. So in this lecture, I'll assume you know what cyclic quadrilaters are. If someone doesn't like, please let me know so that I can like quickly tell you in like a few seconds because I won't be doing so later. What cyclic quadrilaters are, what some famous centers of triangles are, such as orthocenter, centroid, circumcenter, incenter, and some basic properties related to those. Basically, whatever we covered in the last session should be enough. Some basic properties related to those. What is the one? Mainly that. And in this lecture, I'll try to motivate that what do we actually mean by angle chasing? Like how to spot the angles or like why is it the most common thing? Sort of try to motivate that. And we'll look at 3 to 4 problems. That's the basic plan. Okay. So firstly, we'll just talk about some angles in the configuration related to some centers of triangles. Okay. So when you see a triangle and a problem, the idea is you should be able to sort of feel that which angles in this problem can you get if you ever want to. Like, I'm not asking you to find all the angles in the problem, but I'm just saying that once you read the question, once you draw your diagram, let's say I'll show you a random diagram. So this is for let's see. Yeah, okay. So this is sort of a diagram from a problem that I made. You probably don't know the problem, but once you draw a diagram like this for you, for whatever problem you're doing, the after enough angle, like showing angle chasing problem, you should be able to feel that which angles you can get in the figure. Like this is in center. So you know like these angles, this angle, and okay, once you read the problem, you know that you know sort of this angle as well, stuff like that. So you should just get the feel of which angle you can get, but you don't need to compute those until you actually need that for a part of the solution. Okay, so let's start with orthocenter. These are our traits of altitude. Can uh, can someone find all the angles in the triangle, like whatever angles you can find? Also, one more thing about angle chasing is, which we'll realize while you solve the problems itself, that once you solve a problem, okay, like we'll do this in this class, that one thing about orthocenter is, if you reflect orthocenter, this is it, reflect H over D or midpoint of BC, like either of these 2 points, then the reflection lies on circumcircle of ABC. Like the thing is, you don't need to memorize this as a lemma. Okay, this is like a full problem in itself, and you might solve this at some point, but you're doing some another problem, and you see, oh, like a reflection of H over D is involved, and I know this lies on the circumcircle. Like after enough practice, such things will just click to you. Please don't unmute if you don't have anything to say. Yeah. Uh, it just breaks the flow. Yeah, I was saying that after trying enough problems, we just try to see these patterns in the new problems that we're trying, which is kind of helpful. And which is why the thing is we recommend you to solve more and more problems. Okay. So that was all the things I had to talk about. Yeah. So find all the angles that you can in this figure. I'll wait for a minute or two. This orthocenter thing, that reflection of orthocenter over these things are on the circumcircle. I mean, if it comes in a question, prove it. It's not hard. Like, why would you risk it? Will hardly take you 2 minutes to write it up. Yeah. Okay. Would anyone like to unmute and tell me the angles in this triangle? Oh, yes. One good thing is, whenever we are writing angles, we'll ideally try to write them in terms of the angles of a triangle. So let's call this C, B, and A. We'll get to that later. First, do this problem. Like, don't rush. I'll do that problem in today's class, but first do this. I just quickly want to do some basic things so that I know everyone is at the same page. So in this problem, I have assumed that ABC are the angles of the triangle, and I want you to find any random angle in this figure that you can find. Like, say this angle, this angle, this angle. I'm telling you that you can find all those angles. Would anyone like to unmute and say? Okay, you don't need to tell all the angles, like at least one or two angles. That would be nice.
Like three basic angles would be angle FHE would be 180 minus A, angle FHD would be 180 minus B, and DHE would be 180 minus C.
Right. And how do you get those?
Because there are three cyclic quadrilaterals because of the
Yes.
right angles.
So you get these angle, this angle, and this angle. I'm not writing what it is. Like, you know that you can find it out. Okay. Um, okay, what other angles? So you know that this is 90. So you can find this angle from triangle ABD. It will be 90 minus B. Similarly, you can find this angle. If you can find this angle, you know AFHE is cyclic. So you can find this angle.
In fact, you can show AFHE is cyclic because AHE is 90 degrees and AFH is also 90 degrees.
Yeah. Like, I just thought that was sort of well known, but I should have maybe said it. Like, AFHE is cyclic because this angle is 90 and this angle is 90. And this is also cyclic quadrilateral. And this is also cyclic quadrilateral. Okay. And now I think you can see that we can find all the angles. Like, let's say we have to find this angle here, right? So we don't have anything directly to find this angle, but if we find the angles of this triangle, this yellow triangle, like the other two angles, I can find this angle, right? And okay, I know this angle. I know this angle is 90 degrees. So I know this angle, right? So I know one of my angles, right? Can I get this angle somehow? This green angle, which is not shaded.
HFE should be HAE, so it is 90 minus C.
It is what? 90 minus?
C.
Yes, because this angle is basically the same as this angle, right? So you can find this angle. So and now then you can use angle sum property and find this angle. So my point is, in orthocenter configuration, you can find all the angles. Okay, I'll just quickly write down some of the angles for people who don't believe me. Although this does seem very basic right now, but don't worry, like we'll get into the problems and stuff pretty quickly. Depends on how interactive you are. So, okay, let's see. This is C. Um, this is 90 degrees. This is 90 degrees minus C. This is also 90 degrees minus C. This is cyclic. So this is 90 degrees minus C. We also get that this is cyclic. And okay, what other angle? Like, is there any nice angle? Someone already told me this angle. Okay, what about this angle? This shaded part of the black angle. This angle is equal to this angle here. And since BFEC is cyclic, this angle is B. So this is also B. Right? So I can just keep on finding all these angles. Okay. So we have a bunch of cyclic quadrilaterals here. The nice thing about cyclic quadrilaterals in this configuration is you know the center of each cyclic quadrilateral. So let's say BFEC, this cyclic quadrilateral. Its center is midpoint of BC because angle BFC is 90. So BC is diameter and midpoint of diameter is the center, right? Can someone tell me the center of AFEH? What's the center of this circle?
Midpoint of AH,
Yes, why?
because AEH is 90 degree, hence
Yeah.
AH is the diameter.
So AH subtends an angle of 90 degree, which means AH is diameter. So midpoint of AH, okay, midpoint of AH is the center of the circle. Okay. So let's move on from orthocenter to now incenter. Yeah. Okay. I'll mark some angles and try to find those angles. Find the yellow angle basically.
So angle AEAFE is equal to 180 minus as half of 180 minus A.
Yes. Okay, just to tell people how it is. We know that A equals to AF in center thing because these two are like tangents to the N circle. So angle AEF equals to angle AFE. And so now you just use angle sum property and this will be 180 minus A by 2. Can you find the other yellow angle as well?
That will be
We can apply X-centered angle theorem.
Sorry, can you repeat? Two people spoke, one of you.
It will be AFE, that is 90 degree minus A by 2, plus that angle FAI, that is A by 2. Means,
Oh, right, you can just do that. That's it. Yeah, by external angle property, like it's just sum of these two angles. This one and this one. That's what we want to say, right? Yeah. So you can find it. I'm not writing the angle, but my point is you can find all these angles. Okay, what is angle DFE? Like, don't tell me the exact angle, just tell me how to find. Like, how would you go about it?
Can you use the fact that DFE is half of DIE?
Sure, you can use that. Okay, that one said.
But then how would we find DIE?
Okay, think about it. It's not that hard to find.
It would be like 180. We have this angle AFE 180 minus E by 2. Angle BFD would be like a 180 minus
Something.
B by
Yeah,
2.
you can find it.
So we
Yes.
can get that third angle.
Yes. You get that this angle is 180 minus b by 2, and then all these angles sum up to 180. For someone who said angle DIE, notice that you also have cyclic quadrilaterals here. So this is one thing about angle changing. You can't miss other facts. Like when you're trying to change the angle, keep all the facts that you have in mind. Like notice that these are 90 degrees. Like that is what basically this circle means. So this is a cyclic quadrilateral as well. Now do you see how to find angle DIE? I think Athar said it, right?
Yeah, it's
Yeah,
100
like
minus C.
Yes. So these are some things I want to point out in angle chasing. Like what that was the purpose of doing this small exercise. First, find cyclic quadrilaterals whenever you can. Like not just blindly go hunting for only cyclic quadrilaterals, but if you see that this quadrilateral looks like cyclic or this should be cyclic, or you just see that this is exactly cyclic. Wow, those are very interesting statements. But yeah, like it should be cyclic or it looks like cyclic or it is cyclic. Like find it out and write it down in your like notes or something. Notes are like wherever you're solving the problem, like make a small box and write down your observations. Uh, remember previous results, like whatever you found earlier, because that is going to be useful. Like you can't be like, oh, like this I need to find, but then you don't remember that you found it sometime back. Okay, like have an idea that you tried to find this stuff. Like so, maybe you have it in your notes when you were trying to solve earlier. Remember previous stuff that you worked on. It's possible that you also failed on the stuff that you were working on. So that can also like help you not waste time on a problem, let's say. Okay. So try to do these things. Right. So is everyone here comfortable with like basically how to find angles? Like it's not that easy always, but okay, what is the problem? Or also like if I'm speaking and you have a question, raise hand. That also works. Aritra? Okay, I'll wait for you to speak, but until then I'll continue. Speak whenever you can. So yeah, my question was, is everyone comfortable with finding basic angles? Which problem? Not in the class. That will take a lot of time. Like I'll have to first think of the solution, motivate it. But you can ask in the server, I mean. Okay, I'll just quickly create a poll. Whoever marks no for the poll, I expect you to at least say what part you were struggling with so that I can sort of guide you in the right direction. But yeah, launch the poll. Okay, only half the class mark. Is the other half sleep?
Oh, it
Yeah,
only the poll has started. It doesn't show the poll.
it doesn't say what?
Oh, never mind, never mind.
Yeah. Okay, two people haven't marked the poll yet. Okay, let's see. Okay, one person said no. If you have any question, like ask away. Otherwise, we'll move on to problems. I'm waiting for the question. Until then, who doesn't have any questions, try this problem. Oh, no. Okay, yeah, try this problem, then we'll go on.
I
And we
think
won't be
this
using, sorry, yeah,
first
go on,
question.
Amit. Go on.
I think this is Sharigan's first question.
Yes, I think all the problems that I took were from Saragan because I was like too lazy to think of other sources. Have you solved this before?
Yeah,
Okay, have you solved problem 4 here?
the last one.
Yes.
No, I think.
Okay, this is also from Saragan, but you can try this problem until we are trying problem 1. Okay, that should be a nice time usage of yours. Okay, I'll slow down the pace as someone asked me to. If you have any questions in the previous part, feel free to ask that. But from now on, I'll slow down the pace. Try problem 4. I'll not be entertaining any like non-class questions in the class though. Like you can ask and ping me in the server if you want to. But keep the discussion related to the topic we are going, as it distracts everyone. For anyone who has solved problem 1, try problem 4. Okay, I'll move to problem 1. If someone solves this problem as well, just let me know. I'll give you another problem. Okay, from people who have not solved the problem, any ideas about how we should approach this problem or what we should try to do? Someone was saying something? Also, for someone who just joined, we have just started this problem. Aritra, you have solved the problem. I asked for people who have it. Try the other problem.
Prove that, let's say, A0, let's say C1, C0, and A0 is collinear. You can try showing that, let's say, C1, C0, A is equal, the angle is equal to the angle.
Sorry, can you repeat? I wasn't able to follow.
So, to show the C1, C0, and let's say A0 are collinear, then you could try showing that the angle C1, C0A is equal to the angle A0, C0B.
Right. Okay. See, that is a good way to go about it. But there is one problem. Uh, see, you know what A1 and C1 are very nicely, right?
Yeah.
Right. Okay. For those people who don't know what A1 and C1 are, notice that AI, like I is the angle bisector. So this angle is A by 2. This angle is A by 2. And since this is cyclic quadrilateral, this angle is A by 2. and this angle is A by 2. So you get this is equal. So A1 is the midpoint of the arc BC, right? Similarly, C1 is midpoint of arc AB. So you know what A1 and C1 are very nicely, right? Now, Atharu, the thing you are trying to prove is C1, C0, A0 collinear, right? In which you don't know what 2 points are. Like you know about how C0 is defined, but you don't know it that nicely, right? So
Yeah.
yeah, so a better way to do is try to prove C1, C0, A1 collinear. And then this will just finish the problem. Why? Because A0 is essentially symmetric to C0, right? Like think about it, it's just a symmetry. So if you prove this by symmetry, this should also lie on this line. If you're not satisfied, you can also go and prove it in a similar way. But if you just prove C1, C0, A1, then this automatically lies by symmetry. Symmetry is also a very important idea in angle change. Like when you have to prove two things, and they are like defined in a similar way. Okay, so you can just say stuff by symmetry. It's a very powerful. Okay, so let's try to prove this. Okay, how is C0 defined? C0 lies on circle AIC1. It lies on the line AB, and we want to show that it lies on the line A1C1, right? So if we sort of like assume, like let's say introduce a point C0 dash. Excuse me. If we introduce the point C0 dash, which is A1 C1 intersects AB, and I prove that this point lies on this particular circle, then this point should exactly be CO, right? Because by definition of CO, it is intersection of this circle and this line as well, right? But that will just solve my problem if I prove that the intersection of these two lines lie on this circle. So is everyone clear with that idea, that what we will try to do?
Yes.
Yeah.
Is A1C1 parallel to AC?
Which ones?
A1C1 parallel to AC.
A1 C1 parallel to AC. Let's see. Might be
No,
true. Possibly not, sir.
not necessarily.
I think I can find these angles. So this is C by 2, A plus C by 2. It doesn't look like parallel. Let me think
Yeah,
of
they won't be parallel.
what?
I don't think they'll be parallel.
Yeah, I don't think either that they would be parallel, but I just want to check that.
They are not parallel in
Yeah.
normal triangle.
Yeah, I got the proof it's not parallel. I'll tell you after the solution if you want to tell the proof. Or you can try to disprove it yourself. But yeah, they're not parallel. Okay. So is everyone clear that what we are trying to do here? So we now let this new point C0 dash to be intersection of this purple line, which I have now basically made a black line, and on AB, and I have to prove that A, C, C0 dash, and I are concyclic. So now I just have to prove a cyclicity. Can you find the necessary angles to prove this cyclicity?
Could you repeat which cyclicity we have to prove?
Okay. Did you get this idea? Like what we are trying to do here?
Yes, I got it.
Yeah. So if you have to solve the problem, on which circle should C0 dash lie on?
It should lie on the like A C I and like the circle, this
Yeah,
circle.
this circle, right?
Yes.
Yeah. So which is the secondary that you want to prove?
That it is
We could
collinear.
prove like
Like it lies. It is collinear to A1 C1.
No, no, no. See, okay. Wait a second. I'll try to motivate it again. See, the initial problem asks you to prove. So C0 is a point which is intersection of this circle, right? Or this circle and this line, AB. This is intersection symbol, right?
Yes.
And I want to prove C0 also lies on AB. Sorry, A1, C1, right?
Yes.
If I introduce a point, let's say C dash, which is AB intersection A1, C1. Firstly, I know that there is only one such point, right?
Yes.
Intersection of two lines. And if I prove that this also lies on this circle AIC1, right? Then I prove that there is a unique point which lies on this, and this thing, right? So now C0, which is defined as the intersection of these two things, would also lie on this thing automatically, right? Because I've sort of proved it from this idea.
Okay, got it. So basically, we have to prove like CO dash lies on that circle. A1,
Yes,
A, I see.
yes. So the idea is we had something like we have to prove that three things are concurrent, okay? And we take any two nice things out of those and prove the other thing passes through it as well. And now it depends on you what two nice things you can pick. That is one very generic idea that is used almost everywhere. Okay. So here I see that these two lines, like A1, C1, and AB, are very nice lines because I just know a lot about them. So if I take their intersection and try to prove a symmetry, it might be nice. It's just an intuition, and you can't directly expect to get it. But with solving problems and trying other things as well, you might eventually come to this step. Is what I want to say. Okay.
actually we have to prove like angle ACI is equal to angle AC C naught dash I, and
Sorry,
angle
can you repeat?
ACI is
ACI.
angle is equal to angle AC naught dash I, not angle ACI, no, angle AC1I
Okay, this angle.
is
You're
same
saying
as
you have
the,
to prove that? Yes, we have to prove this.
yeah, and angle ACI should be angle
ACI should be angle.
B, because AC1C is angle ABC, and basically we have to prove
Yeah,
like
you're saying, yeah, you have to prove that this angle is B. Yes.
that C naught I and BC is parallel.
Is it parallel? Oh, you're saying you have to
Yeah,
prove that it's parallel.
yeah, we have to prove.
Right. Okay, that's a very good idea. But I don't see it leading anywhere else. Like it possibly could have just solved the problem. But right now I don't see it. Let's see, maybe we find some.
Or you could try proving that angle AC1C is equal to
Oh,
angle
Atharv, I know that you have seen the solution probably by now if you're raising your hand. I want others to try it for a while. So it's fine. You have solved the problem, right? Just try this problem for that. Take a screenshot. Yeah.
So can you just go back to the problem for a second?
Yeah. Okay, I don't see anywhere this parallel line leading to B because I know, like, I don't know any relation with CO dash and I, right? So that is okay. Like, it's a very good idea, but that is one motivation to sort of drop it and think of somewhere else if it's not working. Okay, it
Okay,
could.
so
Uh,
we can prove that angle C zero and like I'm calling C0 and C1 actually. Angle C0 C1 I being equal to angle C0A and A1.
Yes. So
And
basically you have to
that's,
prove that this angle is a by 2, right?
yeah, and that's not hard because angle BCAI is also equal to that, and basically
Yes. Okay.
close to that.
So see, we try to use all the cyclicities we have. Basically, that same thing. Don't lose the information that you had earlier. Athar, can you raise down your hand if you don't have anything to say? The information you had earlier was that A1, C1 lie on the big circle. We haven't utilized that anywhere yet. So we try to utilize that now. And we see that this angle is equals to, from this arc, this angle, which is a by 2. And now this angle is equals to this angle, which is also a by 2. So now I have proved A, C1, CO dash I are cyclic. And now I'm done with the problem. So is everyone clear with the solution? I'll just quickly raise a poll.
Can we prove that C0, A0 and C is a quadrilateral?
What do you want to prove?
C0, A0 and C is a quadrilateral.
A, C0, C and
A0, A0 is a quadrilateral.
I mean, why do you want to prove it? It's obviously a quadrilateral, no? Did you mean cyclic quadrilateral?
No, no.
I mean, then it's obviously a quadrilateral. What's there to prove in that? Yeah, anyway. So,
How did you get the A by 2 part?
right, see. So, what was the definition of CO dash? That it lies on this line, right?
Yeah.
So, see the angle subtended by this arc. It subtends an angle a by 2 over here, right? So this angle should also be a by 2.
Okay. Now I
And this
understand.
angle is a by 2 because like angle bisector, right? So we know these two angles. So see, we basically try to use all the info. So after reducing this problem to something new, we are using the information we had earlier in the very beginning of the problem, right? So it's nice to remember that information is the point. Okay. Oh, sorry, I mistakenly closed the tab. Okay. Can you see my screen now?
It's black.
Okay, I'll restart it, but just a second. Yeah, one second, let's quickly raise it. Yeah, you people answer the poll. I fix my screen share. So let's slow down. Just can you see my screen share? I highlight out. Can you see my screen share? Anyone?
No.
Okay,
No.
okay, I'll should I rejoin? Okay, I'll rejoin. Just a second. Okay, it should be working now, my screen share. Is it?
Yes.
Yeah.
Okay. Fine.
Yeah.
Wait, Mandar, are you still posting? Okay, no. Fine. Uh, right. So I hope the idea is clear basically, like what we sort of want to do with angle chasing. Let's do a side problem first. This is a very cool problem and it actually has a name on it of its own. If someone knows it, please don't spoil. So basically what I do is I give you three parallel segments. AB, any three parallel segments, CD and EF, such that this is cyclic and this is cyclic. Prove that this is also cyclic. Yeah.
I know this one. Could you show the next one? Know the solution.
Okay. Have you seen the fourth problem? This one?
Yeah, on the
One
first
second.
problem,
Mandar, have you seen this?
Yes, yes, I have.
Oh, you have seen this one as well. Have you seen
Yeah.
all of these before? Second
Yes,
and third?
yes, I have. Like I've done all the problems.
Okay. Have you done ISL 2019 G1?
Yes, I think it was an EGM.
Okay, you have done most of it. I think you can leave the class if you want to. I don't have
Okay.
many problems for today.
Okay.
Yeah.
oh, Pranav, Bhaiya,
Yeah.
the problem 4 that you gave, I feel like there's a mistake in the problem.
What do you think is the mistake?
This is the reflection of the Orthocenter.
People, one second. People try this question, by the way, and don't listen to that discussion for a while. But yeah, continue. Athar.
It says that when you reflect the Orthocenter about the circumcenter lies on BC, but due to symmetry, shouldn't it also lie on, can't also lie on AB or AC?
No, I mean, reflection of orthocenter over circumcenter does not always lie on BC, but with some special angle condition in the triangle, it is possible it lies on BC. Like it's just one special triangle.
This is a special triangle.
I mean, obviously, it can't, like in any triangle, it can't lie there. So, like I'm telling you, there is a triangle like this in which it lies there. Yeah. Okay. And Athar, if you haven't solved this problem, solve this first. That is just a bucket problem.
I've solved this problem before.
Okay, cool. For other people who have not solved this, any ideas?
Yeah, so AB is parallel to CD and parallel to EF if that's not already given.
Oh, sorry. Can you? What did you say?
Like the three segments are parallel. Like, is it already given?
I didn't understand anything after parallel. Can you repeat? Sharanya, what did you say? Sorry, I think I pronounced it wrong. Oh, you're done. Yes, the information is given. The three segments are parallel, and you have the two pink cyclic quadrilaterals. I want you to prove that the yellow quadrilateral exists as well.
Sir, BDF and ACE are same angle.
VD,
BDF and ACE are same angle.
you are saying,
BDF.
okay, this angle and
Sorry, BDF. BDF
yeah, VDF
and ACE
why are they
are
same?
same. Why are the same? Because ACDB is a isosceles trapezium and DCEF are isosceles trapezium.
Yes. So we have two isosceles trapeziums. So we have that this angle is equals to this angle.
Yes, yes.
and this angle, which is this. For someone who does not know about cyclic isosceles trapezoids, I think every isosceles trapezoid is cyclic. Take it as an exercise and prove nice facts about isosceles trapezoid. I'm pretty sure it's in school NCRT, unless they've reduced it. So I expect you to know that. But yeah, since these, yeah, it is there. Okay, nice. Since the sum of, so like sum of these two angles are equal, so this angle is equal to this angle. And now since we know that these are isosceles trapezoids, these segments have equal length, right? Sorry. So triangle BDF is congruent to triangle ACE, which means that
Yes, sir.
AE and BF are of equal length, which means ABFC is also isosceles and it's cyclic. Okay. So this is like a cool theorem. It's called Reims theorem. You don't need to memorize the name. You can if you want to. But the idea is if you have three parallel segments and two pairs of those make cyclic quadrilaterals, then the third pair also makes cyclic quadrilateral. That's the idea behind it. Okay.
Can I say
Okay.
that, sir? Can I say that isosceles trapezium is also a cyclic quadrilateral?
Yeah, I said that when I was saying the solution. Any isosceles trapezium is cyclic because you have this angle is x, this angle is also x, and by parallel, this angle should be 180 minus x. So now since these two angles sum up to 180, it is cyclic.
Okay.
Okay.
Bhaiya,
Yeah.
can we use somehow that the three lines are parallel, so they meet at a point at infinity and using radical axis? Can we prove?
Yes, I think that proof should work. Probably. Wait. I think that should work though. Yeah, that does seem correct, except the fact that I don't know if you can use radically axis in the projective plane as well. I'm not too sure about it. I'll ask someone who knows projective plane better than me and let you know. But according to me, it should work. Okay, but don't think that it's correct until I confirm with that. Okay. Uh, what do people want to do? This problem or some Sharagan problems from here? This problem is also an EGMO as I think solved example. So you can see that if you want to later, but I don't mind doing it in class either.
A Sharadan program would be better.
Yeah, that's what I think as well. But I'll just take a quick poll.
That's a problem.
Yeah, that's what I want to do as well. But I'll just create a poll. Yeah, okay, I'll create a poll. You can answer it. Okay. That's much more than majority. So, yeah. This one is a nice problem. Okay, I think this one will give you a lot of ideas. I think all the problems. Has anyone seen this problem before? I think this is also on the recent sharing. Okay, so let's try to draw a diagram, which will be very messy for this problem. This is the center.
Could you show the problem again?
Oh, yes, sir. Is it now fine?
Yeah.
Okay. So I have ABC as a triangle. I have in circle A1, B1, C1. P is a random point on this circle. I draw AP and intersect it with the circle AB1C1, which is this green circle, and call it A2. I draw B2 and C2 similarly as well. I'm not drawing it right now because it will make the things messier. So now I have 3 points, and I have to prove that the circumference of those 3 points touches omega. Firstly, it looks very scary because A2, B2, C2 are like very convoluted points, and then you're talking about its circumcircle, which is even worse. And then you have to show tangency, which is generally a hard thing, according to me at least. So it looks a very hard problem in the first glance, but this is actually very easy once you see the solution because it involves a lot of things which you have seen before. So it also depends on sort of like memory, I guess. Okay, but the thing I would say is when you see a problem like this, when you are defining points in relation to A, B, and C individually, one thing is don't draw all those 3 points. First, just draw one of those. Like I drew A2 and try to get information about one particular point. So like if I nicely characterize this A2, I can use that same characterization for B2 and C2 as well because of symmetry, right? And that just makes the problem much more simpler. So now my focus is just to find nice things about it, nothing else. And I don't even know what those nice things could be. That's just my idea. I have to find nice things. Okay. Also, someone said me to go slow. Is the pace now fine or should I be slower? Okay. So any ideas from people? Okay, and before that, if I'm not saying, see, I drew I in this configuration, even though it was not mentioned in the problem. Why did I do that? Because firstly, the problem was talking about in circle. Like it's a nice circle, and the center is also nice. So why would I not want to introduce I? I should introduce I without reading the problem further. It is possible that it will be used somewhere, like most of the times, at least at the level that you will be giving competition in the next year. So introduce I does not hurt. Okay. Uh, Next thing, if I see the circle A, B1, C1, the green circle, it passes through I. That is a well-known fact. Like we were discussing about it, this configuration sometime before. There. Yeah, here. Right? Like if you discuss about this configuration, you should know. Like we talked about the CDEI circle. It's just this circle. It passes through I. So another nice thing about I, like I is immediately used in the problem. So why not introduce I? That is just like very basic motivation to introduce I, and you should introduce it. Like it's possible that it's completely useless afterwards, but for me, it is very much in the picture right now. So I might as well just mark the lines. Okay. Sure. Does anyone have any random observation? I'll wait for 4 5 minutes.
If AP cuts the encircle at Q, then A2 is the midpoint of PQ.
What A2 is midpoint of?
PQ, where AP intersection of
Okay,
the
why is that?
because IA2 is perpendicular to AP. So
Yes, why did you not say that first? See, Ekagra, I'll say one thing. That's very correct. Like what you said is completely correct. But firstly, we don't even need Q in this problem. Like introducing that is not leading us anywhere, right? Because we just want to see how A2 looks like for now, right? Like even P is useless for us. The only thing which matters is A2 in the problem statement, right?
Yes.
Yeah. So think about that. I'm not saying to think more, but you should have said that as well, is what I'm saying. Okay. But yeah, 10 points to Gryffindor. That's a joke. No. Yes. So you said that this is perpendicular, right?
Yes.
Yes. Because in this circle, green circle, I know that IA is diameter. That is another thing that we talked about in the configuration. Like someone said about this angle, A1I B1, and we talked about this diameter angle there, I think. If not, then that should be like sort of what you should know in general while solving a problem. So since this is the diameter, this angle is 90, right? Which means now I can introduce A2 in a, or okay, let's not go there. But see, I know that this angle is now 90, right? IA2P. So uh, if I consider the circle IA2P, then, or okay, let's not talk about this. Let's draw B2 now, because this is just a nice way to characterize things. So what I can do is, I can draw BP and draw perpendicular from here. And this will be my B2, right? Does everyone agree with this?
Yes.
Yes. Okay. Can someone tell me anything nice in this configuration? Like some new fact.
This is a cyclic quadrilateral.
I A to B to P is a cyclic quadrilateral.
Yes, I guess people are trying to say that four people tried at the same time. But yes, I A2 P B2 is cyclic. But what is even cooler about this quadrilateral? That IP is the diameter, right? Like now, so basically A2 lies on the circle with diameter IP, and I and P are 2 points which are not related to A2, B2, or C2. Like they were existent before these 3 points were even defined, right? So by symmetry, B2 and C2 also lie in the circle. So now I know that my circle A2, B2, C2 is just circle with diameter IP. Is this clear?
Yes.
Yes.
Right. And now the problem is trivial because now you just have to go like for any random point P, circle which is like the diameter of this thing, which has diameter as IP, is tangent to incircle. Like this is an obvious fact, right? Like, I mean, it's that obvious, I don't even know how to prove it, which is kind of interesting now that I think of. It's sort of like distances, but I mean, it's intuitively clear. Like, I don't want to formalize it because I'm lazy to get a formal argument. But the main idea is like this. Yeah, go on.
Can we say that
Aritra, I can't hear you. But yeah, it's like this. You have a circle, you take a point, and like, okay, even if not this, you can have something like this as well. I is the center of the yellow circle, M is the center of this circle, and if okay, I'm stumbling at this point. How do I state this? So much to visualize what you put in words. Okay, I'll just go on with the normal problem and then sort of prove it first. Okay, so take a point, take any other point on the circle. Let's say some point Q, then I know MQ is equals to MP, right? And since I and P are collinear, yeah, it's just like, I don't know how to formalize it, but it sort of makes intuitive sense. Like the minimum distance from M to yellow circle is along the line MP. Sorry, IM, which is MP. So anything which is the same distance as this, but in any other direction, will not pass through the circle because this distance is literally the minimum. That's the idea behind it. But it also just intuitively looks true that if these are collinear, this should be tangent. Okay, this does not sound convincing, but I'm pretty sure that this is a formal proof and this should work. So try to digest it later. But is the idea behind the problem clear?
Both the circles should subtend 90 degree, so they should be tangent at P.
What did you say?
Like the tangent of P should be the radical axis because both the circle are.
Yes, yes, that is also valid too. But I don't want to say radical axis stuff right now. But okay, you can just do this as you said about the tangent. Draw tangent at P to the black circle. It will be a line perpendicular to the line PMI. But since we know that it is collinear and it's a tangent. Okay. Do you see the proof? I'm stumbling in saying it. But like,
This is
since P is
NCERT, I
a
think, tangent proof for 10.
okay, then why do I even need to say it? But yeah, anyways, like P lies on the yellow circle as well, and it's a 90 degree. So the two circles share the same tangent. So they should be tangent. But okay, is the main idea behind the problem clear? The main idea is you had three similar points, like symmetric in the triangle. So you just think about one point. You try to find nice properties about that point. And when you find those nice properties, you combine all the 3 points and get something. That is sort of a very generic way you can go about such problems. I mean, at least in easier problems, that should work. Okay, now let's create another poll. I just like poll because I get the idea of the whole class. Otherwise, it's just like 2, 3 people speaking. Okay, bye. Okay, I launched the poll. And now we can do the next question. Okay, one person has not answered the poll. Wait, this is fine. Okay. So yeah, has any of you seen this problem before as well? Yeah, I should have not picked problem from this one contest. No, in hindsight, that was a bad decision. Right. So this is my problem. Is the problem statement clear to everyone? ABC is a triangle. L is the arc midpoint of AC. It's like the green lines are equal. I draw tangent at L and I draw perpendicular from B onto that line. That is P. I have to prove P, L, and midpoints of BC and AB are concyclic. So that's my problem. Okay. Okay,
Can you
this
show the
is
problem?
this is the problem, no? Written over here. Okay, in this problem, the thing is we don't know anything about P. So there are two ways to go about it. Either we find something nice about P, that's possibly the only way to go about it, I guess. Or also about the line BP, because that's the only line related to P. Yeah. So try to find nice things about P and BP. And because I know that in this problem, you also need nice things apart from those two things. So any nice thing that you find, just tell that. Okay. But mainly try to focus on the line BP and point P.
Can you show the problem statement?
Uh, it's here.
It is not visible. Actually.
Is it not? You copied it. I did add it though. Can you see it now?
No, I think you need to scroll up a bit.
Is it visible now? Is my screen share messed up? Okay, I'll restart screen share because I'm literally showing the problem there. Oh my god, it's just some issue with my internet. Um, Okay, can you see my screen now?
Yeah.
Yeah.
Okay, I also sent the problem in the chat, but I think you can see it now. Okay, so see, firstly, this is a commonly known fact, but I won't be surprised if you don't know it right now, but you should know it in general. The tangent from the midpoint of the arc is parallel to AC. So PL is parallel to AC. I'll just tell you as a fact it right now, but you can try to prove it later. And yes, someone was speaking.
And FD will also be parallel to
Yes,
tangent on three lines.
yes, because midpoints. So by midpoint theorem, FD is parallel to AC. So we have three parallel segments from now. Okay, now since this is parallel and this angle is 90 degrees, which means this angle is also 90. So this passes through the foot of altitude. Let's call this HB, right? Okay, so we have three parallel segments and we have to prove some cyclicity. So it sort of does give Reams vibe a lot. Okay, so if you sort of introduce a new point on this segment, let's call that point X, somewhere, some nice point, just that this is cyclic and this is cyclic, then you're done with the problem, right? The thing is, you can't really chase angles with P directly because, excuse me, that's a bad point to chase angles with. Like it's just intuition. I don't know how to explain it rather that. Like if you try to find let's say angle FPB or FPD, that won't work. It might work, but with a lot more effort. So you should try to find something better ideally when you see such a thing. Okay. With practice, you will see that okay, these angles are very hard to find or close to impossible to find. So this is what we're trying to do. We're trying to find a new point here. Okay. So we have to find a point such that this is cyclic. Can someone tell me what this point could be?
The midpoint of AC.
Yes. How do you get that?
Uh, it is well known that it lies on the circle of FDHB.
Okay. Yes. Or you can just
And
draw this circle and try to find some nice thing about this. Like,
yeah,
you know that
uh,
this angle is 90, so this will be 90.
BP is parallel to the perpendicular bisector of AC. So
What? BP is parallel to the?
perpendicular bisector of AC.
Yes. Why is that helpful?
Sorry.
Oh,
Sorry.
yeah, I asked you to find nice facts about
Yeah.
BP. Yeah. That's fine. That's a good fact. But I think that the thing we had just solves the problem. But that's a good fact nonetheless. Okay. So now we know that this point is midpoint. So what's left in problem? We have to prove F, D, M, and HB are cyclic. Right? Does everyone follow? Does anyone have a doubt right now? Okay. And this is also well known. Like it's just the 9-point circle, but I won't leave it there. I'll give you a nice angle chasing proof for this. So what I want to prove is suppose I have some triangle ABC. I have the feet of altitude as D and I have midpoints M, N, P. And I want to prove this is cyclic. We'll just prove this using angle chasing. Not that hard. We can try to prove it. That this is cyclic. Yeah, actually, now I don't see why this is cyclic. Like, I know that there's a proof along these lines. This is sad. Well, just try to do it. Mhm.
I think I have proved using angle chasing.
Okay.
We know that AP is equal to PD and AN is equal to ND.
Oh, yes, yes. I forgot. Yeah, because this is parallel and it's like half. So
Yes.
you know that this, if you introduce this point, not which, let's say T, then these two things are equal, right? So,
Yes.
and this is also perpendicular because this is 90. So you now know that this length is equal to this length. And then you can probably just finish easily. Because now this angle is same as this angle, which is 90 minus C. So this angle is same as C. Oh, even better. Like N is the circumcenter, like angle ADC is 90. So N is the circumcenter of this triangle ADC. So you can just directly get it off from there. That this is C, so this is C. And so you need to prove that this angle is C. But this angle is B because parallel, and this angle is A because parallel, like these two lines are parallel. So this angle is C. So you get that this is cyclic, or you can just directly finish it in 9-point circle. So like this problem was not very hard if you know the things from before, because everything that we use was just sort of well known from before. The only thing was like try to see that you have three parallel segments and you need to introduce this one more point to finish the problem. Right. So geometry is a lot about taking patterns from practicing problems. Like no one would, like, I would not expect someone to tell you this, that, oh, remember this, that this is a nice thing. Like, that is not how it works. You just do a lot of problems, you see patterns, and you're like, oh, okay, I know that something like this is true in this configuration. And then you see, oh, in this problem, that just fits in very well. So, yeah, that's how geometry works. Okay.
Well,
Yeah.
how often should we try trigonometry here?
Never. Unless you are learning how to bash and you're preparing for a contest, which is for a hard contest, which is in a few months, you shouldn't bash. Like I bash a lot, but my idea is only when I'm practicing bashing, I'll think about bashing that time. Like there would, when I was still contesting, I would take out a week for practicing bashing, and in that week I'll just see any geometry problem, I'll try to think about a bash solution. But apart from that week during my preparation, I would like mostly think of synthetic solutions unless I see a quick way to bash it out. I'll try to think of synthetic only. So I think you should never do trigonometry unless you're learning that skill. Yeah. Okay. So I hope that this problem was clear to everyone. I'm not doing a poll because if someone has it out, you can ask it. I also don't want to do that another problem because I have to go at 8:30 and it will take a lot of time. So I can put that in the preset. It's a nice problem. What I can do right now?
Sir, we did not receive the PSETs on invariants, I guess. Will we get that soon?
Yeah, I remember that preset. Okay, I'll just end the class and then talk about it.